variable stars are a concept in astronomy. Um, they're basically just stars that change their brightness. So stars quite literally twinkle, but these variable stars don't twinkle in the same sense that when you go outside and look at a star, it's literally like flickering. Variable stars vary their brightness over longer periods of time than the twinkling stars you see in the sky. That twinkling is due to atmospheric turbulence affecting the light. So most stars are variable. Even the sun is. It changes its brightness by about 0.1% every so many years. And there's many different categories and classifications for stars alone, let alone variable stars. This star here, it's called SS Cygni, is the one that I will explain a little bit about in a little bit. And you can see that it has a flicker, if you can make that out, in the center of the image. This image was taken these are two images that are being animated together. One was taken June 1st, and another was taken August 7th. So this star varies by about, it has a period of about 2 months variation. And this diagram here on the right is a bunch of classifications of stars. The ones I will be focusing on is on the bottom right, which are called white dwarf stars and red dwarf stars. So SS Cygni is what's known as a cataclysmic variable star. And the reason why it's called cataclysmic is because it usually consists of two stars. It's called a binary star system that are orbiting each other and essentially erupting every now and then. And specifically, SS Cygni is a dwarf nova because it's two dwarf stars. SS Cygni is near the constellation of Cygnus. It's a circumpolar constellation, which means that at any given point in the year, the constellation is up, so therefore the star is up most of the year. A way of measuring the light from stars in astronomy is called the magnitude scale. So in the magnitude scale, the lower the number is, including negative numbers, the brighter the object is. So in this scale here, the sun is about roughly negative 27 magnitude, and the dimmest object your naked eye can make out is about 6 magnitude. And SS Cygni tends to vary from 12th magnitude to 8th magnitude about every 2 months, about every 7 to 8 weeks. But the keyword here is tense, and what I wanted to do with this summer is to test that theory and see if that trend is consistent. So the method I'm using to do this project is called differential photometry, and it asks a fairly simple question: how bright is this star compared to that other star? So there's a bunch of photometry software online, and what all of these do is they convert pixel values of stars in a given image into magnitude values. And an example of how the software works typically is, let's say here's an image of Cygnus, and let's take the star all the way on the left, the 1.3 magnitude star. And let's say we know that, and that's the typical magnitude that star is, but we measure it in our image. The software gives us 1.6. 1.6 minus 1.3 is 0.3, so all of our other measurements of other stars will be off by 0.3. And typically, we use something called the comparison star, which is a star of well-known magnitude that doesn't fluctuate too much. And if the software is given the magnitude of that star, it can calibrate essentially for the rest of the stars in the image, and then you can know how bright the star that you care about is. And that's exactly what I'm doing this one. And we can use this data that we get over multiple nights to form something called the light curve, which is just magnitude as a function of time. So this is a light curve of SS Cygni from the early 90s to about the late 90s. And you can can see in the graph that it has a peak of about every 2 months. Down here is the month, is the time months. So about every 2 months it peaks up to about 8.5, 8-ish at some points, and then it goes back down to about 12. So the equipment and routine that I use for this one. So I have to pray that the weather is nice most of the time, and unfortunately this summer it hasn't been that great. There's been rain, there's been the smoke from from Canada. So all of that has been really messing with my product. So I don't have much good data, but I have some data that I still need to process. So my equipment consists of a telescope, and a camera, and an electric filter wheel nowadays. So originally I was using something called a CMOS color camera, but traditionally for these measurements, CCD monochrome cameras, which is basically no color cameras, are typically used, and CMOS cameras are kind of a newer way of doing it. So there's less data for those ones. And then another thing I also use in the lab is filters. So I use 3 specific filters: UVB, U standing for UV, B standing for blue, and V standing for visual. And what these filters do is they basically only allow certain wavelengths of light through the filter that can hit the camera. So U is for UV, V is for blue. Visual covers green all the way to about yellowish orange region of the electromagnetic spectrum. So on a good night, I'm out there in front of Victor Stillman actually, from about 6 p.m., 7 p.m. to 3 a.m. The earlier hours for various calibration images. So basically, I take pictures to get rid of dust specks that might be in my image, get rid of noise, inherent noise from the camera. Temperature also affects the quality of my images as well. And then from about midnight to 3 a.m. is the optimal time for me to observe my star of interest, because that's when it's about directly overhead of where we are. And the reason why is because I want to catch the star through the least amount of atmosphere as possible. So relatively speaking, the immediate area is pretty flat. The Earth isn't flat, by the way. But relatively speaking, if you look anywhere that's not straight up, basically, you're going to be looking through more atmosphere. So I want to image this star through the least amount of atmosphere as possible, and that is directly in. So after taking these images, we have some data now. We have some calibrated data. Are we good to go? Can we just, put this on a light picture? No. Light pollution is a problem. It's not as bad here as it is in New York or Vegas. But light pollution is a pretty big problem for things like astronomy, and it can even has implications for wildlife and human health in some cases. So this is a pretty big problem. What do we do about our measurements then? What can we do to avoid this problem or fix this problem? And what we can do is something called aperture photometry. So this is basically an extension of the differential photometry method. And the crux of this is that the software will make 3 rings around a given star that you click on. So the outermost region defined by the outer annulus and the inner annulus, this sort of donut on the outside there, is what's known as the sky annulus. And the purpose of that is to collect all of the data from the pixels that represent just the sky. And then there's a region between the inner annulus and what's called the object aperture. That other donut is basically the software ignores that part because that is the sky and also glow from the star. We don't want excess glow from the star. We want the star itself, and that's what the object aperture is for. The object aperture measures the the light from the actual star itself. And then when we have data from the actual star, and we have data from whatever the sky is doing, we take the star data, the aperture, and the annulus data, the sky, subtract it, and now we have our actual calibrated value of that. And this method isn't perfect, but it's a pretty good approximation, as most things in physics and math are. And the software I'm using is called Aperture Photometry Tool. It's free. It's accredited by NASA and various other astronomy organizations. So now we have clean data to make a light curve. So unfortunately, none of this data is mine. But this data is from a bunch of members of the American Amateur Astronomical, or not astronomical, American Amateur Variable Star Observer, the association of one of those things. I forget what it's called. There's so many different organizations, NASA, so but we can kind of see that the trend is fairly similar to the graph we saw earlier. But it is its period is a little bit shorter. It fluctuated from 8 back to 8 again in about a month or so. And this peak here is a little low, it's at 9. So pretty interesting. So what can we do with data like this? Well, we can contribute to astronomy and astrophysics databases, and we can actually make a good contribution to science. And why are we dependent on amateurs for this? Well, there's simply just not enough professionals out there. There's not enough astronomers, and they don't have unlimited amount of time to collect all this data and make all these observations. So we rely on data from amateur astronomers. And amateur astronomers are pretty passionate about what they do. So the data that they submit is probably going to be either good quality, or they're going to make sure that they stress that everyone is in agreement on the data that they get. And with this data, we can help figure out what's going on with these objects. We can understand the universe a little better. We can even detect planets that are in other systems out there. Depending on how much the light dims, we can say, oh, that's probably a planet transiting. And some future goals that I have is, hopefully, I get some actual data, some good data, and I need to conduct a proper mathematical analysis of the light curve of SSC. And on the side, a supernova was discovered at the beginning of the summer, actually right before the summer semester started. So this supernova is in the Pinwheel Galaxy, which is a galaxy in the constellation of Ursa Major, aka the Big Dipper. And it's about 21 million light years away, so we won't have to worry about it. It's not the end of the world. It would have to be within like the 200 to 100 light year range for any significant effects to have here. And here's a light curve of that. We can see how people started scrambling to collect the data in late May, because it was just discovered then. And we can also see that the light curve peaks at around 11 magnitude and then starts dimming down to, right now it's at about 11.5. Oh, and I didn't make this clear earlier. The green squares are the V filter, and the blue stars are blue filter, and very rarely UV light data is collected, but the light blue sphere, there's actually one that I'm pointing down here, is for the, I want to thank Dr. Fadum, the Fadum lab members, Benji, he was the former class president, he trained me on using the telescope and whatnot. A few other people, physics department, biology department, thank you guys for letting us use the gas tank room to put the mountain. Picking that thing up that thing is like the weight of like a bike, like probably a little